Hey, welcome to The Explainer. Today, we're diving deep, and I mean really deep, into a kind of microscopic detective story. We're on the hunt for these tiny, invisible flaws, you could almost call them ghosts, that are hiding in the very foundation of our entire digital world, the silicon computer chip. So let's get our investigation started.
I mean, just think about that for a second. What if a single, solitary atom, missing from its post, could bring your whole system crashing down? It sounds like something out of science fiction, right? But it gets right to the heart of what we're talking about today. You see, the world of microelectronics, it operates on this scale of almost unbelievable perfection. And when that perfection is broken, even by something as small as one atom out of place, the fallout can be massive.
So this brings us to the core of the problem, these ghosts in the silicon. Our whole world, your phone, your laptop, the most powerful supercomputers on the planet. It's all built on these thin, shimmering disks of silicon called wafers. And as we're about to find out, these wafers can hide some pretty critical yet totally invisible flaws. To build a computer chip, you have to start with a crystal of silicon that's so pure it's almost flawless. But, almost is the word doing all the work there. Because when you zoom all the way down to the atomic level, tiny imperfections can sneak in. They're like ghosts in the machine, before the machine is even built. And these little ghosts can cause some really, really big problems down the line.
Okay, so if these culprits are invisible, how in the world do you find them? Well, we start by treating the silicon wafer itself as our crime scene. And on this crime scene, we've identified two primary suspects. A couple of main types of atomic-level defects. At its core, the problem is actually pretty simple to picture. Our first suspect is called a vacancy. So imagine a perfect brick wall, but with one single brick just gone. That's a vacancy. Our second suspect is an interstitial. Now imagine that same wall, but someone's wedged an extra brick between two others, pushing everything out of whack. Both are super tiny, but they're incredibly disruptive to that otherwise perfect crystal structure.
Now here's the really interesting part. These suspects, they're not just scattered around randomly. Thanks to a 1999 research paper that used wafers from a company called MEMC Electronic Materials, we know they have preferred hangouts. The vacancies, those missing atoms, they love to cluster right in the center of the wafer. Meanwhile, the interstitials, the extra atoms, you'll find them mostly hanging out around the outer edge. This predictable pattern, well, that's the #1 clue our detectives are going to use. So let's get this straight. If you can't see these atomic-level flaws, not even with a standard microscope, how on earth do you find them? Well, you get clever. You build a trap. Or in this case, you build a tiny electrical detective that's sensitive enough to literally feel them.
And our little detective? It's a surprisingly simple electronic part called a diode. You can think of it like a one-way valve or a turnstile for electricity. It lets current flow through easily one way, but blocks it from going the other. Now, here was the crucial insight the researchers had. The way electricity flows through this diode would be incredibly sensitive to its immediate atomic neighborhood. In other words, the diode could feel the flaws right next to it.
The experiment they set up was just so elegant. Researchers at the University of Illinois took one of those wafers, the ones with the known defect pattern, and they built a whole grid of these tiny diode detectives right on top of it. Then they just went down the line, they passed electricity through each and every diode and carefully measured how it behaved, basically creating an electrical map of the entire wafer, one detective at a time. And this brings us to the most exciting part, what I like to call the electrical interrogation. Every single one of those diodes is about to be put on the spot. It's asked a very simple question. Hey, what do you feel around you? And its answer isn't a word. It's a measurement of electrical current and resistance. And the answers they got back were just stunning. It worked. It absolutely worked. When they took all that data from all those little diodes and mapped it out, a pattern emerged that was so clear, so undeniable, it was a breakthrough. The electrical behavior was changing, and it depended entirely on where the diode was on the wafer. The results couldn't have been clearer.
right in the center of the wafer, where we knew the vacancies, the missing atoms were, the diodes showed higher electrical resistance. It was harder for electricity to get through. But out at the edge, where the interstitials, the extra atoms were dominant, the diodes showed lower resistance. Current could flow much more easily. They had done it. They had found a distinct electrical fingerprint for each type of atomic ghost. And here it is, my friends, the smoking gun. This is a quote taken right from the research paper. It says they saw a shift in the IV curve, which is just a fancy way of saying a graph of how electricity flows. And they concluded that the reason for this shift was the radial defect gradient. In detective speak, that means they proved the electrical changes they were seeing were caused by that specific bullseye pattern of defects. Case closed. They had found their ghosts.
So, okay. An academic experiment from way back in 1999. It's cool science for sure, but why does it matter to you today, right now? Well, because this fundamental discovery is, and I'm not exaggerating, a cornerstone of the modern world we live in. It's all about quality control at the most basic level imaginable.
So here's the big takeaway. This research proved that these invisible atomic-level flaws have a real, tangible, measurable electrical impact. But more importantly, it showed that you can use clever, simple electrical tests to find these flawed spots on a wafer before you spend millions or even billions of dollars trying to build a complex chip on it. This principle, this ability to find the ghosts before they cause a problem, is a huge, huge reason why the incredibly complex electronics in our pockets and on our desks are so unbelievably reliable.
By figuring out how to interrogate a single material, literally one atom at a time, we laid the groundwork for the entire digital age. It just leaves you with this amazing question to ponder. What other invisible worlds are we just now learning to explore? And what incredible new things will we build with what we find there? Thanks for joining us on The Explainer.